Hello, physics people. I'm going to continue sound today. So here we go, part 2. So, if you burp, you produce a sound pulse that goes out in all directions. Name Barney. Each particle moves back and forth along the direction of the motion of the expanding wave. So as you can see in the picture here, that's how it works. Very mesmerizing, isn't it? All right. You can see a picture of a wave right here. The wave is moving in this direction towards the right. Okay. If you were looking at the length of the wave, right here is what you would look. This part here, where it all bunches up, is called the compression. And this part here, where it is all kind of spread out, is called the rarefaction. Compression travels along the spring similar to the way a sound wave travels in air. So sound wave travels similarly to this compression. The expansion is a rarefaction. As a sound or source of sound vibrates, a series of compressions and rarefactions travels outward from the source. What is sound? So another picture here, you can see the wavelength here. You can see where it condenses, also called compressions. You can see where it's rarefaction, spaced out. How we hear sound. So this is a picture of the human ear. So as you can see, the sound that comes in moves to this part of the ear called the pinna, moves down the ear canal. This is the tympanic membrane, the eardrum right here. Couple little inner parts of the ear, the malleus incus, the stapes, the cochlea, and that's the auditory nerve. So people who get hearing loss or their hearing fixed, they might get this replaced right here. It's called a cochlear implant, and right here is where they might get their sound back. Okay, a lot of inner ear bones also inside the ear. All right, I'm going to do a couple more pages. Sound requires a medium to travel through the medium. Oh, the medium can be solids, liquids, and gases. Sound can't travel in a vacuum as there is no medium to vibrate. So in a vacuum, you will not have solid, liquid, or gas, so you will not have sound. The speed of sound in a gas depends on the temperature of the gas and the mass of the particles in the gas. The speed of sound in a solid material depends not on the material's density, but on its elasticity. In solids, the atoms of matter are packed close together and respond quickly to each other's motions. Loudness. Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a physiological sensation sensed in the brain. The unit of intensity for sound is called the decibel. So that's how we measure sound. It's in decibels. After Alexander Graham Bell measured by oscilloscope. So you can see some of the levels here. You have the jet engine at 30 meters. That is 140 decibels. That's the loudest. Our threshold of pain is 120. Loud rock music, 115. That's probably where I lost a lot of my hearing. Really low ones would be a close whisper at 20. Normal breathing at 10. Some of the decibels for hearing. Physiological hearing damage begins at exposure to 85 decibels. So this is where we start after a prolonged hearing loss. Okay. All my concerts, your loud headphones, those are all cause you to kind of lose hearing over time. So it's not going to get better than it does now. It'll only get worse, your hearing. Natural frequency. When any object composed of an elastic material is distributed, it vibrates at its own special set of frequencies. A natural frequency is one in which minimum energy is required to produce forced vibrations. It is also the frequency that requires the least amount of energy to continue this vibration. A forced vibration occurs when an object is made to vibrate by another vibrating object that is nearby. Sounding boards. They are an important part of a musical instrument. Force strings into vibration and produce the sound. Resonance. The frequency of a vibration forced on an object matches the object's natural frequency. The forces increase in amplitude. Interference. There's constructive interference occurs with sound waves. The listener hears a louder sound. When destructive interference occurs, the listener hears a fainter sound or no sound at all, so such as we would get with, say, noise cancellation headphones. So looking at this picture here, you have two identical transverse waves in phase produce a wave of increased amplitude. So here you go. This plus this gives you really big waves. Then in B, you have two identical longitudinal waves in phase produce, two identical longitude waves in phase produced a wave of increased amplitude. So see, you have here all these compressions. And then C, two identical transverse waves that are out of phase end up destroying each other. So these ones are out of phase. And then in D, two identical longitudinal waves that are out of phase destroy each other. So you can see like where this one dips, this one goes up. So that's where they're not in the same phase. They're not syncing with each other, and that's why they'll cancel each other. Same thing here. Compressions are, those are opposite of where these compressions are, so they end up destroying each other. Okay, so I'm going to show a couple of videos tomorrow because this screencast is probably long enough, and I know longer is not necessarily better. So I will see you again tomorrow. Bye.